Okay. So in the previous part, we've seen the replica trick, and in the second part of this lecture, we derived the properties of the resolvent and how to obtain from the resolvent the spectral density. So this was done for Hermitian matrices. In this fourth part, we're going to derive the sort of tools that can be used to study non-Hermitian matrices. So for Hermitian matrices, as you know, all the eigenvalues are real. And in that case, the resolvent was a complex function. In this case, the eigenvalues of non-Hermitian matrices are complex, and the resolvent is going to be a quaternionic function. So I'm going to discuss now what are quaternions as a sort of extension of complex numbers, and then I'm going to simply define what is the quaternionic resolvent and how can it be used for non-Hermitian matrices. So complex numbers can be defined simply by introducing a number, I, with unique properties, I squared equal to -1. And then all the algebraic properties of complex numbers derive from knowing that I squared is equal to -1 and that associativity, commutativity, and the distributive properties hold for sum and product. Okay. Oh, sorry. Sorry for that. For instance, the sum of two complex numbers can be given simply by using the distributive properties and the commutative properties, and knowing that how to sum real numbers. And similarly, the product can be obtained in a similar way, knowing that I squared is equal to -1. So as soon as you know complex number, you can express any number as the sum of a real number plus a real number times I, and you can introduce as definition the conjugate of a complex number, z bar, as x minus iy, where you basically change the sign of the imaginary part. So then the absolute value of a complex number is simply the product of the complex number times its conjugate, and these absolute values is a real number, always positive, and it is easy to see that the inverse of a complex number can be written as the conjugate of the complex number divided by the modulus. Moreover, a complex number can be represented as vectors, where the entries corresponds to the real and the imaginary part. Okay. Similarly, quaternions can be defined introducing three symbols, I, j, and k, with the following properties. So that I squared equal to j squared equal to k squared equal to ijk, all equal to -1. So from this equation, you can derive the following multiplication rules, that ij is equal to k, jk is equal to I, and ki is equal to j, and ji is equal to -k, kj minus I, and ik minus j. So the main difference between complex number and quaternions is that in quaternions, multiplication is not commutative. So in fact, ij is equal to k and ji is equal to -k. So they're not equivalent. A quaternion can be always represented as a sum of a real number plus a real number times I plus a real number times j plus a real number times k. And there is also an alternative, more convenient representation. So using the fact that k is equal to ij, you can always write a quaternion as a complex number plus another complex number times j. And the mapping is written here. So a plus bi in the quaternions is the first complex number, and cj plus dk can be written as c plus di times j. Great. So it's important to keep in mind that since I and j do not commute, a complex number times j is different from j times the complex number, because when you multiply j with I is actually equal to minus I with j, so a complex number times j is equal to j times its conjugate. And again, we can apply the associative plus the commutative properties for the sum, and the product can be derived using the properties that we defined earlier. We can also define the conjugate in a similar way, simply by taking all the signs of the numbers that are not real and changing their sign. And so then we can express it as also in its complex representation. And again, as you can imagine, the product of the of a quaternion times its conjugate is actually commutate, and is equal to the modulus of the quaternion that is a real positive number. And again, as in the case of complex number, the inverse of a quaternion is unique and can be written as the conjugate divided by the modulus. One can also introduce, and we're going to use that, the element by element multiplication. That is the one obtained by simply multiplying the real part with the real part, and the part proportional to j with the part proportional to j. So complex number can be represented as vectors. Quaternions can be represented as 2 by 2 matrices. So in general, a quaternion equal to z plus wj as the following 2 by 2 representation. And all the properties of the sum and the multiplication that I explained above are equivalent and simply follows from matrix algebra. And so the element by element multiplication, it corresponds to Hadamard product, which corresponds to multiplying matrices by multiplying their entries. And also an important connection is that the number I and j and k, when expressed in matrix notation, corresponds to, are actually proportional to the Pauli matrices. And so everything can be also explained as the algebra of Pauli matrices. Great. So now let's use quaternions to define the resolvent of non-Hermitian matrices. For non-Hermitian matrices, the eigenvalues are complex. So when we define the spectral density, we should define the density on the complex plane. So we have actually a combination of two delta functions. This is the empirical spectral density. S is the size of the matrix. And we define what is the density in this complex plane. So the non-Hermitian quaternion, non-Hermitian resolvent is just the same function that we derived earlier, but instead of having real eigenvalues, we have complex eigenvalues, and instead of having complex numbers as an argument, we have quaternions. So this is just a definition, and it's easy to see that the resolvent can be expressed in terms of the spectral density, and in an analogous way, it's easy to obtain that the spectral density can be obtained as a limit of a derivative of the resolvent, where we have to take the derivatives over the conjugate of the complex number. We can be expressed as the combination of the derivative of its real and imaginary part. So using this simple expression, we have this quaternionic resolvent, and we can apply exactly the same methods that are used for Hermitian random matrices for non-Hermitian matrices. And so one can extend the replica trick to study non-Hermitian matrices, but there are also other methods that are actually discussed in depth in the book I suggested at the beginning. And just to name them, the cavity method, which assumes that the matrix is a tree, there are no loops. The Coulomb gas methods, which start from the full joint probability distribution of eigenvalues, and is a method to marginalize over the distribution, and others, they all take use of the resolvent, and all these methods can be generalized to the non-Hermitian case using the quaternionic resolvent. So this is all for the first lecture. So as I anticipated, in the next lecture, we're going to look at some cases with the motivation of community ecology, and we're going to discuss some application in that context, where we also will take into account non-trivial network structures. So thank you very much for your attention. Thanks.